Good morning, everyone. For this short video, I wanted to go over this handout. Normally we do this one in class, and I like to start with part 2 because I think it's important for us to get rid of our numbers dependency. That is, we are so used to having numbers when we do mathematics that whenever we see a problem that has no numbers, we tend to freak out thinking that's going to be very hard to do or even impossible. However, if we know how to get a solution using just variables, that solution will apply to any situation that is similar or identical, regardless of the numbers. Whereas if you plug in your numbers right away, then your solution, your final formula, it's only good for that problem only. So let's begin. We have, using the graph shown below, figure out everything you can about the motion. When you see this sentence, what the on-ramps people are saying is they want you to develop a full model. So let's take a look at this graph. We have a velocity versus time graph, and we have this point here, this one, and that's going to be our initial velocity v naught. I know it's already here, but I'm just going to write it here. That way we know. And then we know this point over here, this one, is the final velocity. Also, we know that this is the initial time we're going to assume is 0. Normally, it is always 0, okay, unless otherwise stated. And then we have t final over here. This is t final. For consistency, I'm just going to call it t, because we don't use the f or the I. We use naught, the little 0, and then when there's nothing next to the letter, that means it's the final one. Okay. Well, what else can we find? By now, hopefully you completed the reading, part 1, and you know that acceleration can be defined as the rate at which velocity changes. And then I want you to look at these two words. Rate changes. That would be rate of change. That is the slope. So then we can say that the slope of this line, the velocity graph, the slope of this line represents acceleration. Just like the slope of a position time graph is velocity, well, the slope of an acceleration time graph, the slope of a velocity time graph is acceleration. Furthermore, we can even find displacement. So the area of a velocity versus time graph, that represents the displacement, delta x. So when they say figure out everything you can about the motion, normally that means we're going to find initial velocity, final velocity, acceleration, and displacement. And of course the time interval, which we have over here. And because there's no quantities, we cannot find any numerical answers. However, we can find an equation that will give us acceleration. Let me explain. Think about this line in terms of math. If you wanted to find the slope, you would need to find the coordinates of this point, the coordinates of that point. So let's do that. Well, the coordinates of the initial velocity would be the x is always time. So time would be t naught, right? That's this point here, on the x. And v naught would be the y coordinate. Because t naught is 0, so we did not move anything along the x, and we just moved 1 along the y, because this point represents v naught. Likewise, for the final velocity, along the x we moved t, right? Because t would be here, whatever this represents t. And then upward we moved all the way up to v. If that's a little confusing, don't worry. Right now when we put in numbers, you'll see how that makes sense. So these are the coordinates for this point where we have the initial velocity, and these are the coordinates for that point where we have the final velocity. To find a slope, we can use this formula. And I know all of you remember that one from algebra. So we'll make this one x2, y2, x1, y1. Okay? The slope will be the acceleration. So that means acceleration is going to be y2, that is v final, minus y1, that is v initial, divided by x2, that is t final, minus x1, that is t initial. And this one can be written as the change. That's delta. That triangle means delta. That is change. Or you can think of it as final minus initial. That works in physics. Change in velocity divided by change in time. This is actually the average acceleration, but that works just for general acceleration as well. Just slightly different. Okay? So remember, this one is average acceleration. So then we can say what we found is that the acceleration is delta v or delta t. All right, what else can we find? We can use the general formula for acceleration, because if t naught is 0, we get rid of this term, right? So we can say this is v minus v naught divided by t. So let's solve for v, just because. Let's solve for v. The first thing we'll do is multiply times t. Next, I'm going to add v naught. Then I'm going to use the reflective property. That is, I'm going to put this on the right side and this on the left side. And there we have it. We have a second equation. This is the first equation we found. This is now the second equation. And let's use the fact that we said the area underneath the curve is the displacement. Well, if you think about it, this is a trapezoid, a right trapezoid. This is base 1 or base A, base 2, base B, whatever you want to call it. And then this would be the height, okay? So the area of a trapezoid would be 1/2 base 1 plus base 2 times the height. Now let's substitute our variables. So the area would be displacement. So we'll say this is delta x. Then 1/2 is just 1/2. Base 1, let's call this one base 1. But what is the length of base 1? Whatever v naught is. Whatever the value for v naught, we would plug that in. So we can say v naught plus b2, base 2, that would be whatever value we have for v final. And then the height would be the time interval. Because we're assuming time initial is 0, whatever this number is the total time, so just t. And that is another equation. So these two equations, guys, are part of something called the kinematic equation, or the equations for motion with uniform acceleration. And then the last one, I'm going to give you another one. To derive that one, we would need calculus, but this class does not use calculus, unfortunately. So I'm just going to give it to you, okay? With a little bit of calculus, we can find the displacement to be initial velocity multiplied by time plus 1/2 times acceleration times time squared. So if we had values, which we will right now, we could find acceleration. Initial velocity is going to be given to us but we can also find displacement. So when they ask you to figure out everything you can, or build a model, full model, they expect you to provide initial velocity, initial time, final time, acceleration, and displacement. Those 6 quantities should be included in your model. Okay, let's box this one. Although you should know all 4 equations, the ones I'm going to highlight are the ones called kinematic equations, and we're missing one of them, but it's fine. You'll read about them later. So now we will apply all this when we have numbers. I'm going to write everything I know, but I'm going to replace it with numbers. Okay, so I have added all the numbers that I know. 0 seconds for T naught, 6 seconds for T final, 9 meters per second for final velocity, 3 meters per second for initial velocity. And then I also copied the equations we derived on the previous page. So now let's find out everything we know. Let's start with the initial velocity. Well, that's given to us. Initial velocity is 3 meters per second. Final velocity is also given to us. That's 9 meters per second. We can find the acceleration using this formula. And I'm going to use the average one, okay? So just to use T naught. Although we would get the same answer for this one, I'm going to use this, meaning that I'm going to use this version of it, the one with T naught. Now I just have to plug in my numbers. And then 6 divided by 6 is just 1. Then the units, if you know how to do a unit check, please do that. That's going to help you a lot, especially for unit 2. So that's going to be 1 meter per second squared. If you don't know how to do a unit check, just ask me when I come back. Ask me, and then I'll show you how to do that. I'll show you how to get meter per second squared using these two, okay? All right, so now we have the acceleration. Well, we use time initial, that's 0 seconds. Time final, 6 seconds. Let's find the displacement. For the displacement, you can use whichever equation you want from these two. However, I'm going to use this one just to show the trapezoid, and then we will plug this in into the calculator just to prove that we're going to get the same thing. All right. Let's plug in our numbers. 9 plus 3 is 12, times 1/2 is 6, times 6 is 36. So the displacement came out to be 36 meters. The reason why we get meters is displacement is a vector and its magnitude is distance. So we want to know units of distance. That is just meters, okay? Meters is the unit we use for distance. If you don't believe me, let's use decimals. When you plug in anything on decimals, do not worry about the units, just the numbers. 9 plus 3 times 6. 36 is expected. Okay, now let's use the other equation just to prove that it is 36. When you plug in numbers, be careful with the squares, okay? So the square goes to the entire time, so that means it has to be outside the parentheses. Let me show you the implications when you do that on decimals. So we start with 3 times 6, that's in time, plus 1/2, times 1. Now it's not 1 squared. The square belongs to the seconds, not here. It's inside the parentheses, so it does nothing. However, for this one, the square would go into the 6 and into the second, meaning that you have to have 6 and then squared. Okay? Again, that makes sense if you know how to do a unit check. Ask me, please. And as expected, it is also 36. And the unit would be meters. So now we know everything there is to know about the motion. We know those 6 quantities. That is initial velocity, final velocity, initial time, final time, acceleration, and displacement. That's how you build a full model based on a graph or a physical situation in kinematics. Make sure you watch the example, as it will help you with your first lab experiment.